by the previous theorem, we only need to show that lambda naught is non-zero, and therefore we can assume that it is equal to 1 by dividing both sides of this inclusion by lambda naught. Okay, so it suffices to show that lambda naught is not equal to 0 in the previous theorem. If the latter's condition is satisfied and x bar is an optimal solution of the problem. Okay, and that is for this direction. Okay, so by contradiction, we assume that lambda naught is equal to 0. Okay, so lambda naught is 0 in this inclusion. Thus, there exists Vi, that is in the subdifferential of Gi of x bar for I from 1 to m, and also V in the in the normal cone to the set omega at x bar, such that zero is equal to the sum of lambda I times Gi of x bar, where I, so over here is Vi, where I runs from 1 to m plus V. Okay, and again over here lambda I are greater than or equal to 0, and lambda I times Gi of x bar is equal to 0 for all I from 1 to m. Okay, then this is 0, 0, the inner product of 0 and u minus x bar is equal to this, the sum of lambda I times Vi plus V, where I runs from 1 to m, and this is u minus x bar. This is also 0, where u is the element in is an element in omega, satisfies the Slater's condition. That means Gi of u is strictly less than 0 for all I from 1 to m. Okay. Now, let me continue this. Thus, we get this. 0 is equal to the sum where I runs from 1 to m of lambda I, and over here this is the inner product of Vi and u minus x bar, okay, plus the inner product of V and u minus x bar. Okay, now because Vi is in the subdifferential of the function Gi at x bar, by the definition of subdifferential, this is less than or equal to the sum where I runs from 1 to m of lambda I times Gi of x, actually u, minus Gi of x bar, okay, plus the inner product of V times u and n u minus x bar. Okay, but this is because of the complementarity condition. Lambda I times gi of x bar is always 0. So this is equal to the sum where I runs from 1 to m of lambda I times gi of u, okay, plus the inner product of v and x minus and u minus x bar. Okay. Now this is less than or equal to 0 because v belongs to the normal cone to the set omega at x bar. So the inner product of v and u minus x bar is less than or equal to 0. And at the same time, because lambda naught is equal to 0, and note that lambda naught up to lambda m are not 0 simultaneously. So over here in this we get that because lambda naught is 0 already, then lambda 1 up to lambda m are not all 0. That means there exists some index lambda I for which lambda I is strictly greater than 0, while gi of u is strictly less than 0 for all I from 1 to m. Therefore, we end up having that this is strictly less than 0. This is a contradiction. So this is okay, and therefore lambda naught has to be non-zero, and again by dividing both sides by lambda naught we can assume without loss of generality that lambda naught is equal to 1. So we complete the first part of the proof. Now let me prove the opposite implication of the theorem. So now we suppose that this is true. 0 belongs to the subdifferential of f at x bar plus the sum of lambda I times the subdifferential of gi x bar where I runs from 1 to m plus the normal cone to omega at x bar where lambda I here are greater than or equal to 0 and lambda I times gi of x bar is equal to 0 for all I from 1 to m. And over here we also assume that x bar here is always feasible. Okay, now we will show that x bar is an optimal solution of problem P. We will show that okay, so fix any feasible solution x. Okay, our goal is to show that f of x bar is less than or equal to f of x. Okay. So now, from this inclusion, we get the following. So then, there exists v naught that is in the subdifferential of f at x bar, and vi is in the subdifferential of gi of x bar for I runs from 1 to m, and v that is in the normal cone to the set omega at x bar such that 0 is equal to v naught plus the sum of lambda I times vi where I runs from 1 to m plus v. Okay. Thus 0 is equal to 0, the inner product of the vector 0, and x minus x bar. Okay, and then we replace 0 by its representation here. Okay, and then by the distributive property, this is just V naught x minus x bar. Okay, and this is the sum of lambda I times the inner product of Vi and x minus x bar, where I runs from 1 to m, plus the inner product of V and x minus x bar. Okay. So now, by the definition of subdifferential, this is less than or equal to f of x minus f of x bar. Okay, and this is less than or equal to the sum of lambda I times gi of x minus gi of x bar. And then we add this. Okay. So by the complementarity condition, lambda I times gi of x bar is equal to 0. So this is just equal to f of x minus f of x bar plus the sum of lambda I times gi of x, where I runs from 1 to m, and this is the inner product of V and x minus x bar. Okay. Okay, because x is a feasible solution, this is always less than or equal to 0. Okay. Now, because V is in the normal cone to the set omega at x bar, the inner product of V and x minus x bar is less than or equal to 0. So this sum is less than or equal to f of x minus f of x bar. Therefore, f of x bar is less than or equal to f of x. So x bar is an optimal solution of P. Okay. And the proof of the theorem is complete. Now, again, to solve this optimization problem, we only need to solve this inclusions. Okay, and in the case where omega has some particular form, we can replace, we can calculate the normal cone to the set omega at x bar. For example, if in this inclusion, if omega is given by this, the set of all x in Rn, such that Ax is equal to 0, and over here A is an m by n matrix. Then we can see that in this inclusion, n x bar omega is replaced by the range of A transpose. That means A transpose of Rm. Okay, and we already discussed this earlier. Okay. Now I'm going to discuss another condition that guarantees not lambda naught is equal to is not 0. So we can assume that it's 1 as in the previous theorem, for the case where all functions involved are differentiable, and also omega here is the whole set Rn. Okay, so now we consider the problem. Minimize f of x subject to gi of x is less than or equal to 0 for I from 1 to m, where f and also g1 up to gm from Rm to R are differentiable convex functions. And we denote this problem by Q. Okay, so now we obtain this theorem. In this theorem, instead of assuming the latest condition, we assume the linear independence of the gradients of the function gi, where I runs in the active index set. Okay? So, consider problem Q and let x bar be a feasible solution of Q. Now we suppose that the set gi of x bar, where I runs in A of x bar, is linearly independent. Then x bar is an optimal solution of Q if and only if there exists multiplier lambda 1 up to lambda m greater than or equal to 0, such that 0 is equal to the sum of lambda I times the gradient of gi at x bar plus the gradient of f at x bar. So we can write like this, is equal to 0. And again, the complementarity condition is satisfied. That is lambda I times gi of x bar is equal to 0 for all I from 1 to m. Okay? So let me go through the proof of this theorem. Okay, so by the first theorem presented, there exists lambda naught and lambda I such that these conditions are satisfied. And over here, because there exists no constraint omega, that means omega is the whole space Rn, this normal cone reduces to 0. So we actually have this. Okay? And because the functions involved are differentiable, this inclusion can be written as 0 is in. The subdifferentials reduce to the gradient. So this inclusion becomes this equality. Okay, and it is also lambda naught times the gradient of f at x bar plus the sum of the gradient of gi of x bar, where I runs in the active index set. Because if I is not in this set, lambda I is equal to 0. Okay, so again, similarly to the previous theorem, we only need to show that lambda naught is non-zero. So by contradiction, suppose that lambda naught, I'm sorry, over here we have lambda I, okay? We suppose that lambda naught is equal to 0, okay? Then this sum is equal to 0, okay? And by the linear independence of the gradient of gi's from here, then we see that lambda I is 0 for all I in A of x bar. Okay, so here, therefore, all lambda i's are 0, which is a contradiction because we know that by the theorem we presented before, lambda naught up to lambda m are not 0 simultaneously. And therefore, this is a contradiction. Okay, and so the proof is complete. And then for this part and for the other part, the proof is very similar to the proof of the previous theorem. That means if this condition is satisfied, then x bar is an optimal solution of the problem. Okay, so again, the proof is very similar to the proof of the previous theorem. So we complete the proof of this theorem. Now I'm going to present a very simple example to illustrate the method of Lagrange multipliers. So in this problem, we have to maximize the function x1 plus 2x2 subject to the condition x1 square plus x2 square is less than or equal to 1. And this optimization problem can be solved by a minimization problem. So this problem is converted to this equivalent problem. Minimize minus x1 minus 2x2 and subject to the same condition. And now we are going to use the method of Lagrange multipliers presented earlier in order to solve this optimization problem. To do so, we define the following function. And also g, here there is only one constraint, so we only use g of x. This is x1 square plus x2 square minus 1, so that we can use the previous theorem. So this is x1 square plus x2 square minus 1. Okay. So for this problem, we can easily see that the Slater's condition is satisfied because, for example, we take x1 x to be 0, then this inequality is strict. Okay, so observe that the Slater's condition is satisfied. Over here, there exists no omega as in the theorem presented earlier. So by the method of Lagrange multiplier, any x bar, any feasible solution x bar is an optimal solution if and only if these conditions are satisfied. So instead of solving this optimization problem, we solve these conditions. And here, because the functions involved are differentiable, we can again replace the subdifferentials by the gradient. Okay, so basically we have to solve this. So 0 is equal to the gradient of the function f at x plus lambda times the gradient of the function g at x. And over here, lambda is greater than or equal to 0. Lambda times g of x is equal to 0. And at the same time, x is feasible. Okay, so now let's solve this using the formulas for the function f and g. Okay, so this is equivalent to 0 is equal to the gradient of the function f is minus 1 minus 2 plus lambda times the gradient of the function g here is 2x1 2x2. Okay, now lambda is greater than or equal to 0 and lambda times x1 square plus x2 square minus 1 has to be 0, and also x is feasible. Okay, so then we get the following. 0 is equal to, this is minus 1 plus lambda times 2x1. And then similarly, here 0 is equal to minus 2 plus 2 lambda x2. Okay. And then lambda is greater than or equal to 0. Lambda times x1 square plus x2 square minus 1 is equal to 0. And x is feasible. Now, if lambda is equal to 0, it cannot satisfy this equation. Therefore, lambda has to be non-zero. Okay? So, because lambda is greater than or equal to 0, it has to be strictly positive. So, from here, we will see that lambda is strictly positive. And so, x1 is equal to 1 over 2 lambda, and over here, x2 is equal to 1 over lambda. And because lambda is strictly positive, x1 square plus x2 square has to be 1. Okay? And from here, if we plug in, we will see that 1 over 4 lambda square plus 1 over lambda square is equal to 1. So, we get 5, so over 4 lambda square is equal to 1. And from here, we can easily see that lambda square is equal to 5 over 4, and so lambda is square root of 5 over 2. Okay. So after we get this, we can plug back here in order to see x. So then x1 is equal to 1 over 2 lambda, that means 1 over 2 times this, so we have 1 over square root of 5. And x2 is equal to 1 over lambda, that means 2 over square root of 5. Finally, we get this, x is equal to 1 over square root of 5, 2 over square root of 5. And we can verify that this x satisfies all conditions here, and it is also a feasible solution. Therefore, it is an optimal solution of the problem. And actually, this problem has a unique optimal solution given by this. Now, let me introduce another example. In this example, we have to minimize the following function: x1 square plus x2 square with the following conditions subject to x1 is greater than or equal to 0, x2 is also greater than or equal to 0, and x1 plus x2 is less than or equal to is actually greater than or equal to 5. Okay. So then this problem can be converted to the following form: minimize x1 square plus x2 square. Here we write minus x1 is less than or equal to 0, minus x2 is less than or equal to 0, and also 5 minus x1 minus x2 is less than or equal to 0, so that we can fit to the form of the theorem presented earlier. Okay, so for convenience, we also write out the so-called Lagrange function as follows: x lambda here is equal to x1 square plus x2 square plus lambda times minus x1, here lambda 1, plus lambda 2 times minus x2 plus lambda 3 times 5 minus x1 minus x2. Okay, and here x has only two components, x1 and x2, and lambda has three components. Okay, now again we can check that the Slater's condition is satisfied, and therefore we can apply the theorem presented earlier and solve these conditions instead of solving the optimization problem. Okay. So then using this and by computing the gradients of the function f and also the function gi given here, we can easily see that we get the following. The partial derivative of the function L with respect to x1 is equal to 0. So 2x1 minus lambda 1 minus lambda 3 is equal to 0. And also the partial derivative of the function L with respect to x2 is also 0. That is 2x1 actually 2x2 minus lambda 2 minus lambda 3 is equal to 0. We also have that lambda 1 times minus x1 is 0. Lambda 2 times minus x2 is 0. And lambda 3 times 5 minus x1 minus x2 is equal to 0. And over here, lambda I are greater than 0. Greater than or equal to 0 for I from 1 to 3. Okay. And these are complementarity conditions. So from there, we see that x1 is equal to lambda 1 plus lambda 3 over 2, and also x2 is equal to lambda 2 plus lambda 3 divided by 2, okay, by these equations. And then we plug back into these equations and we obtain the following. So then lambda 1 times lambda 1 plus lambda 3 is equal to 0. And here lambda 2 times lambda 2 plus lambda 3 is equal to 0. And also lambda 3 times 10 minus lambda 1 minus lambda 2 minus 2 lambda 3 is equal to 0. And also lambda I are greater than 0 for I from 1, 2, and 3. Okay. So let's look at two cases. Now case 1. So from here, if lambda 1 plus lambda 3 is equal to 0. Now let's look at this case. If lambda 1 plus lambda 3 is equal to 0, because lambda I are non-negative, then we see that lambda 1 is equal to lambda 3 is equal to 0. Okay? And then because lambda 3 is 0, we plug back in here, we will see that lambda 2 is also 0. Okay? And because lambda I are 0, then when we substitute into these equations, we will see that x1 is equal to x2 and is equal to 0. But then for this x, it doesn't satisfy the constraint because we see that the constraint, one of the constraints here is 5 minus x1 minus x2 is less than or equal to 0. Okay, so this x is not a feasible solution, therefore it doesn't satisfy. It's not an optimal solution of the problem. Okay, and therefore from this equation, so case 2, we look at the case where lambda 1 is equal to 0. Okay, so if lambda 1 is equal to 0, and similarly to the previous one, we can show that if lambda 2 plus lambda 3 is equal to 0, then we obtain 0, 0, and again it's not an optimal solution. So we also see that lambda 2 is also 0. Okay, so in that case, we obtain the following solution. Then lambda 3 is equal to 5. Okay, because lambda 1 is 0, lambda 2 is 0. And then we see that lambda 3 is equal to 5 because of this condition. How come lambda 3 cannot be 0? Because if lambda 3 equal to 0, then again we obtain x1 is 0 and x2 is 0. So it's not an optimal solution. Okay, so in this case we can easily see that x1 is equal to x2 is equal to 5/2. Okay, and so we obtain this solution. Okay, so over here I believe that we have to solve the systems a little bit more carefully, but ultimately by some simple manipulation we obtain the only feasible solution x that satisfies these equations, and it is 5/2. Okay.